Thank you very much for having me. My name is Feldman. I will give a short update about AV1, VVC, and the current standardization of video codecs, and what is currently going on in the landscape and what is going to happen over the next few years. I work for a company called Bitmovin. So we have multiple products all based around the cloud and video and OTT streaming. One of them, we have a player, analytics and encoding, all based in the cloud. And the last one is my forte. So short introduction about me. I did my PhD at the University of Aachen in the area of video coding. And after that joined Bitmovin. I worked with scalable video codecs, HTVC specifically, so I was also involved in that standardization. And yeah, that's my background, how I got into Bitmovin. So encoders, decoders, and technology and research in that area, that's my forte. A short introduction, a short agenda about the talk. I want to talk a little bit, I want to give a short introduction, a little timeline about the different video codecs, where we are right now, where we're headed. I want to do a little bit of technical background at least, like introduce some unique new tools to the specific codecs, what's really different about them, what's similar about them. Without going into detail too much, because you can imagine video codecs are really complex pieces of technology, and there's so much research and so much detailed technologies in there. So yeah, if you want to talk about that, you can do that for weeks straight. I just want to touch a few big points. And then, of course, I want to talk a little bit about the current state, about the current performance evaluation of the codecs, and give a short overview there. Okay, you don't have to fully understand this diagram. I just want to raise one very important base point, which is hybrid block-based video coding. And this is the diagram for hybrid block-based video coding. And this diagram is basically over 20 years old. So the idea is, the video codec is using blocks, so the whole video frame is processed in blocks, and the whole thing is hybrid. Why is it hybrid? Because we can see here, so the original image comes in here, and then we subtract a prediction signal from it, and the prediction signal comes from either intra-prediction or inter-prediction. So intra-prediction does prediction within the same image, and inter-prediction uses reference pictures from a buffer which have been previously coded to do a prediction. And then, with the error signal, you do a transformation and a quantization. This is where the hybrid comes from, right? Here we are in the pixel space, and here we are in the transform space. That's what hybrid means. And then the whole thing is done in reverse, and everything goes into the picture buffer. You don't have to fully understand what's going on here. My basic point is that this graph is 20 plus years old, and all video codecs which we are using this basic underlying technique. MPEG-2, AVC, AV1, VVC, they're all using this basic scheme of video coding. So also with the more modern video codecs like VVC, we're not seeing a reinvention of the wheel. It's basically established technologies just brought to the next level and evolved upon. That's my basic point here. Okay. The two main codecs I'm going to talk about are VVC and AV1, and I want to shortly introduce who's doing these. So for VVC, that is the Joint Video Experts team. So that's the ITU and MPEG who joined together to do this standardization. They also joined together for AVC and HTVC. The standardization goes on through these parent bodies, and if you want to propose something in the standardization, if you want to get your patented technology into the codec, you have to be a member of either of these organizations, and then you can get in and propose something. But overall, it's very open. You just have to be a member, then you can propose stuff. Also, the documentation and the software, it's all open. It's all freely available on the internet. Just go to, there's some links in the references. Go there. You can read thousands of standardization documents if you want to. It's all open. Of course, the goal of the standardization here is always a licensed model. So in the end, you will have to pay for it. That is the idea, right? You get patented technologies into the standard, and in the end, you earn your money back by getting somebody paying for the licensing of that. AV1, that's a little bit different. It's mainly done by the Alliance for Open Media, which is technically a non-profit industry consortium. The main contributors to, especially to AV1, were Google, Mozilla, and Cisco, who were all already working on open source free video coding technologies, and they just joined forces. I don't want to exclude the work of anybody else. There are other companies as well who contributed. These are just the biggest contribution-wise companies who contributed here. Also, the specification and the software, it's all open source. And the idea here is not to make money by licensing the codec. So using the codec is free. You can use it for whatever you like. It's free. But of course, you have to consider both bodies or both standardizations are in it for the money. They're not doing it because of the good of the world. For the companies which are in the AOM, it's mostly they want to save on CDN cost, of course, in the end. So they want to stream the same quality at lower bandwidth and save money, save a lot of money. Just a short timeline. In January 2013, HTVC was finished. In September 2015, the AOM was formed. Between the years of 2013 and 2015, a lot of stuff happened, especially around the licensing with HTVC. You might know up until today, the licensing situation of HTVC is not finally resolved. There's now 3 licensing agencies for HTVC, which do not cover all of the patented technologies in HTVC, which is a big problem for HTVC. AOM was formed, and then shortly after that, the standardization for the next video codec started in MPEG and so in JVET. So in October 2015, then it went the usual way. They do a call for evidence, then they do a call for proposals. Then in March 2018, AV1, the first version of AV1 was published. We're right now here, and the release of VVC is planned for October 2020, the first version of VVC. So, I said I wanted to go a little bit, at least a little bit, touch a little bit some of the core technologies which are different or similar between the different codecs, and I'm going to start with AV1, just a few of them. As I said, everything is block-based, right? So let's start with that. How is an image organized in a bitstream? So basically, each image for AV1 is partitioned into superblocks, which are of size 128 by 128 pixels. These blocks are organized in tiles, so multiple of these blocks belong to tiles. Here we see different tiles. And multiple of these tiles are grouped into tile groups. The tile groups are in different network packages, and so you can easily split an image, or there's multiple things you can do with that, but they are logically split. And tiles can be processed in parallel, so you can do parallel decoding and parallel encoding, but you can't split them on a bitstream level. That's the basic idea. And then each of these blocks is processed in a sequential way, and each block is further split. Of course, 128 by 128 pixels is very big for the hybrid approach, so you do a splitting into even smaller blocks, and that is done using a recursive tree structure. So each block can be split either horizontally or vertically, can be split into 4 subblocks. It can be split like this or this. Those are all of the options that you have, and they are recursive. So the R means this is recursive. So if you split a block into 4 subblocks, then you can, for each subblock, apply the whole thing again. That's the basic tree structure of the splitting in AV1. And then when you're down to the smallest blocks, you do a prediction and then the transformation and all of that. Some of the key technologies in AV1. So what is really new? There's overlapped prediction. Up until now, basically also for HTVC, blocks are discrete. So the border of the block determines a hard border. which is not something which happens in natural videos, right? There's usually not like a border around like blocks, so usually everything flows into each other. And the overlap block motion compensation wants to get rid of these hard block boundaries a little bit, because what happens often is that, especially at low qualities, this is the first thing you will see, the block boundaries, right? When the quality gets bad, you see blocks, and that's very bad for the visual impression of the video. So in overlap block motion compensation, you basically increase the block size a little bit. So this is the original block size, and then you just increase the block size a little bit for the top and left blocks, and perform motion compensation also for these areas. Also for the current block, you do the same, and then you smooth everything together. You basically blend the neighboring block into the current one. That's the basic idea. And depending on the block size, this can be up to 32 pixels in AV1. So it can be a very wide smooth, depending on the block size that you're using. Something else, Ffine Motion, that's also something which is pretty new to video coding. It's, traditionally video codecs used 2D translational motion only, so you could, for motion compensation, have square blocks or rectangular blocks and move them around on the screen. That's it. That's the only thing motion compensation could do. You have a reference picture, you copy it, you move it around the block, and then that's your prediction. That's it. But usually, in videos, things don't always just move horizontally on the screen. Things also rotate, things scale, things do different things, right, on the screen. It's not just like translational motion. And that's the idea of Ffine Motion. It's a motion model to map more complex motions into the 2D space. All right, so, and it's usually done by, and these are just, DOF is degrees of freedom. So for 2D translational motion, you have 2 degrees of freedom, which is down here, right? So the original block can move into X and Y direction. That's it. For 4 degrees of freedom, you add more freedom for the block, so the block can also scale and rotate. And if you now even add it up to 6 degrees of freedom, you also get aspect ratio changes and shearing to the block. And when you allow all of this to happen in the video codec, you get an even better prediction, right? In the video, if something really rotates, you can map that to a block, and then you can actually map that in a video codec and get a much better prediction of what's happening, because you can then transmit that in the bit stream. In the bit stream, it will just say, take this block, rotate it, and then you get a much better reconstruction. And the key point is that in AV1, this is implemented using 2 sharing operations. That's also pretty cool. You just take a block, share it into one direction, then share it into the other, and with that, you can map all of this into a hardware and software reconstruction and optimize it using SSIM and all of those technologies. Another thing in AV1 which is new is wedge prediction. I showed that blocks can be split horizontally and vertically using various methods. But again, in natural video, we rarely have edges which are horizontal or vertical. Usually you have diagonal edges, or you have different kinds of edges that you want to adapt to. And wedge prediction is an idea to also get a better prediction, right? So edges, so the idea is you split a block non-square, but using like an angular split within the block. And in this case, you use a code book, and these are the entries into the code book. So all of these are the possible wedge predictions you can use. And for each of the parts, so for the black and the white part, you do a prediction, and then you blend them together. You can see there's like a smooth, it's not a hard edge here, but there's a smooth transition between the 2 areas, and that's the basic idea. And with that, you can much better adapt to natural edges in the image which happen. Another thing in AV1 which is kind of new is CDEF. It's a constrained directional enhancement filter. It's basically done after the image has been reconstructed. You filter it, and with these post-processing filters, which are in the video codecs, the most complicated part is always you want to filter the image. You want to filter out blocking artifacts which might have occurred, or reconstruction errors which might have occurred, but you always want to keep the edges sharp. That's the most important thing, right? You don't want to smooth out the edges because that's the real content, and the artifacts are that's what you want to get rid of. And the idea here is that on the reconstruction, you take, let's say this is our reconstruction, then you analyze if there's a directional property to the block. So you compare it with these directional filters, and then you will find, oh, this is a very good fit. And then you basically apply a filter which filters into that direction along the edge. So you filter out artifacts which are not along this edge, but you filter with it. So the edge stays sharp, and you get rid of any reconstruction errors that you get. And the cool thing is also that this search is done at the decoder side, so you don't have to transmit any bits for this. The decoder just does it. It does the analysis, which of these filters to use, and then he does it. One more, which is really unique to AV1, is the film grain synthesis. Yeah, Netflix, that's right. The Netflix filter is also a good name for it. There's a lot of ups and downs for this, but basically you have three steps that you do. It's on the encoder side, you first remove the film grain and the noise in the image. Why would you want to do this? Because film grain and noise is very special in video coding. It transmits very little information for your brain, right? It doesn't, if there's just noise, you just perceive it as noise, but it's not important for the reconstruction. It's not important how exactly the noise looks like, as long as it has similar properties, right? And that's what this is trying to exploit. So first you remove this film grain and noise, then you encode the video using completely conventional video coding, and at the decoder side, you add the noise again. You add a synthetic generation of the noise again, using some parameters that you transmit. So instead of transmitting the noise using the conventional encoding methods, you just transmit how does the noise look. And that just says it's very coarse and it looks something like this. And then at the decoder side, you can generate a noise which looks very similar to your brain. It's not the same, but it just looks similar. And then you add it on top, and that's it. And this is very unique to video coding. And if you do this right, you can save enormous amounts of bitrate. If you have noisy content, it's easy to save 50 to 60% of bitrate with this, with the same output, perceived output quality. And that already brings us to the problems. The big problems with these are, of course, what is noise? How do I determine what is noise and what is content in the image? How do I remove it properly? How do I model it correctly? And how do I set up all of these parameters and filter it properly? So there's a lot of problems with it. The idea is really cool, but it's not like an automatic solution that you just run through an algorithm and that's it. It's way more complicated than this. But if it's done right, then it can save a lot of data rate. Of course, there's a really long list of other things which are quite new in AV1. There's a lot of new intra tools. There's a lot of new inter tools. Compared to VP9, you have more references. There's a really cool arithmetic coding engine now. There's more transforms, there's frame super resolution coding. There's a lot of additional tools, as I said. We could talk about this for hours or even longer. So yeah, that's about it. I'm going to wrap it up for AV1. And we'll get to VVC. So VVC, right now it's being standardized. So all of the stuff that I have to say is not fixed yet. A lot of it will probably get into the codec like this, but it's still all up for discussion. Something could still get out or be replaced by something else, so this is a little preliminary. But let's start off with the partitioning. So a frame in VVC is split into coding tree units or coding tree blocks, which are 128 by 128 pixels. These are organized in tiles. And multiple of these tiles can be grouped into tile groups where each tile group is in a different null unit. Wait a second, didn't I just talk about this? Yeah, do you also have deja vu? This is really, really similar to how AV1 handles it. I mean, the whole concept with blocks and tiles and grouping them together has already been in HTVC. But this is just, yeah, this is almost one-to-one. It's a little bit different, and there's a lot of stuff which is currently being still figured out how to do, but it's really, really simple. Partitioning. So each of these 128 by 128 pixel blocks is further split into subblocks. How is this done in VVC? They have a really cool method of doing this. So the basic idea is you have the block, and now you have a combination of two steps. In the first step, you have a quad split, a recursive quad split, and then you have a recursive binary or ternary split using very flexible methods. And I'm going to show you an example. So for example, the block, first we decide to split the block into 4 subblocks. Then for each blocks, we can do the same thing again. That's the recursive nature. So we decide to split the top left one again into 4 subblocks. We decide to split that one again into 4 subblocks. And now when we're done with this quad split, we can go to the binary and ternary splits. And also these are recursive. So then we decide to split this block horizontally into 2 parts, this one vertically into 2 parts. This one we decide to split like this. This one we decide to split with a ternary split like this. And all of this is recursive again. So we decide to split that one again horizontally, and that one again using a ternary split, and that one again using a ternary horizontal split. You get the idea. It's all recursive, and it's very, very flexible to adapt to the real content of the video. And then, of course, for each of these blocks, you do the normal encoding steps again. Transformation, quantization, and then put everything into the bit stream. On intra and inter prediction, there's a lot of new stuff happening in VVC as well. There's a lot of more directions. There's bigger blocks for intra. There's a long list of technologies which they brought in. But as I said before, it's all adding up on existing technologies. It's not reinventing the wheel. Inter prediction as well. There's enhanced motion prediction. There's a combination of intra and inter. That's also in AV1. There's a lot of similarities. There's something called overlap block motion. Wait a second. Yeah, that's also very similar to AV1. It's a little bit more hardware friendly because the overlapping area is much smaller. That's much more friendly for hardware decoders specifically, but very, very similar idea, very similar technology. Ffine Motion. Wait a second. I'm feeling like this is all the same. Yeah, they also have an Ffine Motion model in VVC. Which allows for a more flexible prediction of blocks. The only difference is that they do it a little differently. In AV1, the Ffine Motion model is actually evaluated per pixel. And here, with VVC, they have a very flexible way. They basically just signal control point motion vectors and do not apply the modified motion compensation per pixel, but per 4x4 block. This is really helpful for hardware implementations again. If you have an existing hardware decoder, it's usually fixed on blocks and everything is optimized for blocks, and then you can easily change that and modify it to allow for this kind of a fine prediction using traditional 4x4 block motion compensation. One more thing, well, I think 2 more, but then we'll be over with the technologies, is decoder side motion refinement. That's also a really cool idea. Basically, you perform normal bidirectional motion compensation. Bidirectional means you take one reference block from a past reference and one reference block from a future reference or from a frame which is in the temporal future and combine them into your current prediction. And then you do a second step. Around the original blocks and the references, you do a search again. You search again for a better reference. You take a limited set of positions and evaluate the MSE and look which one would be a better prediction. And then you take those and combine them again to form your prediction. The big point here is, all of this is not really new, the big point here is the decoder side. That is something pretty new for codecs and also especially for the MPEG codecs, because if you do something on the decoder side means we don't transmit any information on this, we just let the decoder do it, right? We just tell the decoder, apply this algorithm, and then the decoder has to search, choose the best one, and combine it again. And of course, there's always ups and downs. On the plus side, you don't have to transmit any information for these decoder-side technologies, but on the downside, the decoder has to implement it and do it, and that's computationally expensive, right? There's always a trade-off between these. And there's a lot of more technologies being discussed right now which have computational complexity at the decoder side, but of course, especially the hardware chip decoder designers are never amused when something like this comes up. It's hard for them, right? Because every operation like this requires a lot of transistors, and yeah, they have to come from somewhere. Another thing, triangle prediction. So the idea is here that a block is not always split into horizontal or vertical. Wait a second. Yeah, this is very similar to wedge prediction. Instead of splitting a block just horizontally or vertically, you split it using two diagonal options, which is like this, and of course the other way. And then you combine two references together and you do a smoothing at the edge. Very similar to wedge prediction, just with less options in this case. One last thing for VVC, which I want to mention. VVC is not only focused on conventional 2D motion compensated prediction or 2D video, but they are also there's also some extensions to it, and one is the 360-degree extension. So there's a whole activity going on in parallel which takes care about, or which is focusing on encoding 360-degree video. The most common way to do this is, here on the left we see an example. You wrap the whole video, or you morph, you map the whole video to a 2D image basically, right? So you map the whole space into a 2D image, apply normal video coding, and at the decoder side you map it again to the 3D space. There's typical mappings like sphere mapping or cube mapping, where you map it onto a cube, or there's different mappings like this. And this mapping has a special property. It basically has a wraparound, right? If you go out here on the right, you will come back in on the left. That's the wraparound. And the same goes for the top. Basically, if you go in here, then you will come out here. And if you go in here, you will come out here, right? That's the wraparound of the 3D mapping. And one of the problems is if you apply normal HTVC video coding, the input images are padded internally, so you can do motion compensation from outside of the image. But what the video coder does, it just repeats the first line of the video. But that's not what happens in these specific mappings, but you wrap around, right? And so what they proposed is they adopted technology that can extend the image using the wraparound. So basically, if you now do motion compensation from outside of the image, you will end up on the other side of the image, which gives some gains and yeah, better compression gains, basically. There's a long list of more stuff. There's a long list of more technologies which are in here, not reinventing the wheel, but changing a lot of stuff, arithmetic coding, transform quantization, there's a lot of stuff. There's a lot of more loop filtering, there's palette coding. The high-level syntax is still being discussed a lot. As I said, it's not finished yet. And then, of course, the coding performance, one of the most important parts, possibly. So this is just an evaluation, the latest one from the VTM, which is the VVC test model, version 4, versus HM, which is the HTVC test model, version 16.20. These are still preliminary, so not all of the tools which have been adopted are already in here. And of course, the standardization is still ongoing, right? It's not done yet. And one of the things that was also noticed is that the subjective results of this can also be a lot higher. The same thing happened with HTVC, but that's a whole different thing. What we see here is, of course, PSNR, BD PSNR scores. And the random access configuration is the one which is most important for us, I guess. It's the VOD typical configuration. And what we can see right now is the compression efficiency is about 1 to 3% more efficient than HTVC. At the same time, you have here the encoding and decoding times. So the encoding time is about 8 times that of HM, and the decoding time is not actually that much higher, right? It's just 170%. That's not a big overhead at the decoder side. But at the encoder side, it's quite an overhead. And we'll see another comparison coming up, because now we want to see the whole environment in action and compare it a little more high level. And also, I want to mention one other video codec which is being developed by MPEG right now, which is EVC, Essential Video Coding. Just want to mention what it is, and then we'll compare the performance, and that's it. So the current state, AV1. Yeah, it has been done. The standard is frozen, so now the vendors are open to implement decoders, encoders, and all of the technologies. There's a lot of software stuff going on. Of course, the libAOM is there, but there's also David, SVT, AV1, and Ray-V, I would pronounce it, I don't know.
Some of them are decoder only, right?
Yes, David is only a decoder, this is an encoder, and this is also an encoder, yeah. And of course, there's other non-open source projects. A lot of manufacturers mentioned that they are also working on technologies, but of course, that is not open source, and we can't really take a look into that. A lot of support is now there. Chrome and Firefox does support it. There's a YouTube page you can just go to and watch AV1 videos if you want to. VLC FFmpeg has support for it. Also in operating systems and in hardware. Of course, this is all still in beta, but most of the companies are working on this. There is, however, no wide adoption of this yet. Actually, I would have been surprised if, it's a little over a year now. For video codecs, it always takes time until there's a wider adoption of it. But it's going, it's starting, and it's looking good. VVC, of course, there's only one reference software implementation yet. The standardization is still going on. There's also no adoption yet, of course. The standardization is still in progress. The reference software, as I said, is open source and all of the documents. So if you want to take a look at that, please go ahead. It's all on GitLab. The licensing situation. Yeah, that's a big one. And actually, I'm an engineer, so I'm just gonna try to state facts, or mostly facts here. For VVC, of course, the standardization is still going on. It's unknown. We don't know. It will not be free. You will have to pay for it. How much? Nobody knows. One of the problems is that the HTVC situation, that's what I called it, could repeat. So in the standardization body, no change to the standardization has been done. So it could theoretically happen that the same thing with HTVC happens again. No measures have been done to prevent that, unfortunately. Also, JVET is not directly responsible. They are just a technical committee. They just think about the techniques. They don't think about patents. So the responsible ones would have been the parent bodies, but nothing changed there. There's the Media Coding Industry Forum, which is trying to promote VVC and try to think about how to implement licenses, but they don't have any real power. That's the biggest problem. They can only propose, bring together, and talk to people, and try their best. Yes, please.
The question that everybody is wondering is that if you separate the technology development from the legal part, right, you cannot prevent the case of a single company claiming to have IP and refusing to be licensed, which is part of the problem with HTVC, right? And that's still doable legally today with VVC. As opposed to our media, where even just taking the membership and not providing any technology to the table prevents you from suing anybody else, any other member, for the technology that are being discussed. So if you don't tie the technology development with the copyright and the IP, the same problem can repeat again and again, isn't it?
That's the big problem. There is, in the standardization, there is one incentive. If you propose a technology which would go into the codec, you have to sign a waiver which says, I am willing to offer licensing for this technology within a reasonable time and with reasonable licensing terms.
But for HTVC, for example, there is 4 groups, 3 different pools, and then one group of company that claim to have IP but refuse to give a franc.
Yes.
So that is happening today.
Yes. The problem is they also signed this, and now the good question is, what's reasonable, right? Is it reasonable to not publish licenses 5 years after the standard was done? Probably not, but nobody went to court so far to challenge this.
The only thing is now you need to go to court if you want to
Yeah.
enforce that.
Yeah, basically, yeah, which is a ridiculous situation. Of course, you're still, yeah, I'll just go on. With AV1, the basic idea is the licensing is supposed to be free. So if you want to become a member of the AOM, you have to sign a waiver saying, if I have patented technologies in AV1, everyone will always be allowed to use it for free. That's the, from my non-legal standpoint, the interpretation of this. You might have heard that there's a third party offering license for AV1 now. But that's about all we know so far. The status of their claims is unknown. There's no patent list. There's no, there's nothing. So we don't know what this means. That's basically it. However, AOM has a patent defense program, so the companies put aside some money to challenge whatever comes up. But that's all we know so far. And of course, what you also mentioned, one of the big points. Somebody jumping out of the bush and claiming, I have a patent which applies to these video codecs and I want your money, that can happen to any video codec. That can also happen to HTVC, AVC, or MPEG-2, or that might have been a little late now, but...
Right, this is happening with the one right now with Orange and TT and the third one, I don't remember,
yeah.
going through an Italian company.
Yes.
But the AOM answered within a week.
Yeah.
And Cisco and the other guys were not happy and they have quite a few patents to oppose back to this.
Yes, so that's basically the patent defense program. Yeah. They have money and IP, and so they are willing to take these guys to challenge the whole claims, but so far we don't know even the scope or what's going on.
I think
that's basically
for them to try to sue any of their users in court, and then they would go there.
Probably, yeah, we'll see. One last thing I want to mention, the essential video codec. Another video codec which is standardized by MPEG. They passed the first CFP stage now and it's in standardization. The idea here is that the video codec has two profiles, which is a baseline profile, which is royalty-free. So they're taking care of only using technologies which are royalty-free. And there's a main profile, which is not royalty-free, but where every tool can be switched back to a baseline configuration. And this gives them the incentive, after the standardization is done, to get a timely availability of licensing terms, right? So if like a company says, "Nah, we're not going to license this technology," then they can just say, "Okay, we're switching it off. You're out." That's the basic idea. However, I see a lot of problems with this as well, because especially for backwards compatibility, what are you going to do if, like, after 2 years you switch off a tool, but you have a bit stream where the tool is used? And then you build decoders which don't support this tool anymore, then you can't decode it anymore. I don't 100% understand how they really want to implement it in the end. Yeah, but that's EVC basically. And now, there's another quite recent evaluation. It's by Technicolor. There's a link also in the references to the data, which compares AV1 with this git hash, the VVC test model, and the EVC encoder compared to the HM reference. And that's really interesting. But of course, I want to give a, and also meant a little bit ironically, warning. The interpretation of the results can lead to wrong conclusions and should always be performed at your own risk. Comparing encoders is hard. It's really hard, and you can get to really wrong conclusions depending on what you put into it, how you configure them, and how you do the comparison. It's really complicated, but still, here are the results. So what can we see here? We can see AV1 is reported to have around 20% gain compared to HTVC. VVC is reported to have around 30%, which matches the previous results, right? They claimed 32%, here it is 30. Yeah, it's roughly the same. And for EVC, they're currently seeing like 16, a little bit less, like 15% BD rate gains compared to HTVC. And also the encoding times, you can see libAOM got a lot faster from previous versions. So AV1 and VVC were about the same encoding speed. For the decoding time, AV1 was a little slower. It's a good question how to again, interpretation of these results can be dangerous. This is of course using the reference decoder. There's much more faster decoders out there.
You have the number with the interval?
You mean SVT?
Or AV1, SVT, AV1.
No, sorry. This
You
is
can expect 10 times faster on the same hardware.
would be interesting to
The
know.
quality
But
is approximately the same. The size is 18% bigger, but it's not real time. It's 7-second latency.
okay. It would be interesting to also include that in a comparison like this. Okay, just one last slide, and then of course I hope we have a little bit time of questions at least. The end. As you can see, there's multiple high-performance codecs in the loop. AV1 is out already, but VVC and EVC will be finished next year, so 2020. But of course, which one to choose is highly dependent on your application and what you want to do and what target your application is. So the big point I want to say finally is, we're heading to a multi-codec world. So one codec will not be able to stream to all users. The times of AVC are over in that regard. I just want to point to some other presentations here, right? I think Twitch, they're talking also about multi-codec world and multiple codec live streaming and things like that. They're preparing for the same thing. I just want to hint there's going to be some other presentations on that if you're interested. Yeah. The last hint to point out that I come from an academic background. References, references, references. Thank you. And of course, questions, yes.
Forgive if this sounds a little simplistic for this, correct? Because this is not my field, but is this presentation presupposing that one or both of these, both AV1 and VVC, is going to replace HTVC? In other words, does HTVC have a limited lifespan, given that these two are rising?
That could happen.
It could have, because you didn't include HTVC in much of this. So I was just curious as to, is the state of HTVC in danger? And the fact that the royalty situation is so confusing makes it even more in danger, in line with the cleaner lines that these two seem to present?
Yes, I think definitely. I mean, again, it depends on your use case, what you're trying to do. But I guess a lot of manufacturers or a lot of guys from the industry are also here are thinking about, yeah, why not? Why do we do HTVC? Let's just skip that and wait for the next generation, maybe AV1 or VVC when it comes out to overtake that and just skip it. Yeah, it's a very interesting question. I'm not good with predictions though.
Well, I just wasn't sure if that was a presupposition in the industry or whether or not that is, as you say, it's just unknown at this point.
Yeah.
If HTVC gets this royalty shit together, could that then solve?
No, it's too late.
I think
It's too late for
It's too
AVC.
late. I mean, I work for a manufacturer, it's too late. It's done deal. I mean, HTVC will never be anything more than a niche codec.
But it's already included in the AVC 3.0, right? I mean, that will last for a long time.
Yeah.
I agree. I mean, it's another vendor. It's embedded in broadcast because it's in the chipset to set up boxes. But yeah, I think it's pretty much there.
Yeah, it's just, I mean, it's unfortunate.
It's a technologically, it's a really good codec. Just, yeah, the whole licensing situation got it by the legs.
Unless they just completely do a, switch and make it so attractive that, they can reverse everything. But I just don't see that happening.
Yeah, but we have no reason to think VVC is going to be any better.
No, we don't.
So,
That's what MCIF is trying to solve.
Yeah.
say it again?
That's what the media coding industry for is trying to argue at the moment.
Yeah, but
Try and
the
stop
person
the
said they've
industry
got no
from
team
again.
in their base. No, they have no control.
Yeah.
Yeah, and in the meantime, Apple and Samsung are taking our media membership.
Yeah. I mean, in the absence of a vacuum, it's going to get filled. Someone's going to fill that vacuum.
I think everybody's keeping their fingers crossed on AV1 that AV1 will not run into issues, right? I think it's big companies supporting it. that's the hope. I think we still don't know, because the licensing has to come after you, after you deploy it, right? So,
Yeah, but, it's interesting that Christian started out by saying all codecs work the same, and he pointed out numerous instances where AV1 has advancements that are the same in VVC. AV1s are either patented and owned by AO Media members or not, and VVC is using the same techniques in many cases, so it looks like there's going to be a lot of issues with it.
Especially in the patent world, it's always hard because you have patents which are kind of vague in some regards, and so which can apply to a lot of stuff or none of it. Yeah.
So we might see AOM people suing VVC for patents.
Or vice versa.
We might see AOM companies suing VVC for patents or creating a patent pool on VVC.
Yeah, it's a great time to be aware.
Yeah.
At the creation of Omega, the intent was really to stop people suing each other, right, and to make it incentive. When you look at the pool of big companies like Omega, they already have a lot of patent by themselves. You have all the big guys. They spend the first 18 months doing all the legal work to clear every single algorithm. The system level block diagram is the same, but the underlying algorithm, there is 50 shades of grays for each of them. And some are patented and some are not. So they went through every single small sub-algorithm to clear them one by one. Are they old enough that they are public domain? Do we have the patent, or and so on and so forth, right? So they didn't start encoding or anything before they clear. So to go back to VEC, for example, there was something called NetVC within the IETF, which had the same target, to have a codec that would have a base that is royalty-free. They stopped it because they couldn't put the same amount of lawyer money to actually clear that the base was actually royalty-free for sure, and who would commit to defend that if someone was coming to sue, which will happen eventually.
Can I open just the floor up for any non-patent related questions or questions, so we can, any other questions that aren't legal in nature? Okay, why don't we wrap this up?
Yeah. Thank you very much for having me, and thank you.